Welcome to a lesson with Dr. Powell. Let's take a look at how we can um, write a multivariable polynomial like this one um, in terms of a, a linear, a bilinear, and a trilinear transformation. Okay, so we have a linear part to kind of you look at these exponents, ones. Okay, you look at a bilinear part, the sum of exponents in each term is 2, bilinear, and this would be trilinear. So linear, bilinear, and trilinear. These are all results of these types of transformations. Which linear transformation would this come from? Well, one way of doing that is we can take this linear part and we can think of the um, first derivative matrix, total derivative matrix of this guy right here, of just thinking of a function from R2 to R, where the output is just x plus y. So let's just think about that. Think about the first derivative. So when we do that, we take a partial with respect to x, and we get a 1. Partial with respect to y, we get a 1. And then the input is just going to be xy. We have just described this first part as a linear transformation. So the linear part is done. Now what about this as a bilinear transformation? Well, let's take this x squared plus xy as a function, and now think about its second derivative. Okay, its first derivative would be, we take a partial with respect to x, which would be 2x plus y, partial with respect to y, which would just be x. Now, we think of this and we take as a function, and as a function, we kind of think of this in terms of columns, okay? And like 2x plus y, and then x like that. And we take a derivative of a partial of that with respect to x, and we put it right here in the first position, just like partial with respect to x, partial with respect to y, partial with respect to x, partial with respect to y, same thing over and over again. But here now we're going to think of it like this. So this partial with respect to x would be 2, 1. Partial with respect to y would be 1, 0. This and the last input that we had, this xy, notice how we turn this on its side? We would like taking a transpose of this right here. So we've kind of taken the transpose of something like notice right here we had 2x plus y and x, and um, and this part. And notice that I'm kind of and what I'm doing is I'm actually thinking a little bit about the I'm thinking about the multivariable Taylor expansion, and this where it's centered. It's actually centered at x and y equaling 0 here. Notice I don't have things like x minus a appearing here. I just have x's and y's. So I'm thinking about, and whatever that means with Taylor expansion here. But just notice, because this is just x and y, we're going to kind of think about things centered at 0 when we plug in 0. Now, if I plugged in 0 here, I'd have a 0, 0. Notice that this part right here at 0, 0 has a 0 first derivative. That's why I could just focus on this part right here and just ignore everything else, because everything else had a 0 first derivative. But if I plug that in, if I plug in values for x and y here, and x and y actually is what the variance from whatever I plug in, like maybe this is like put an x, maybe an x naught, y naught, x naught here, and I plug in an x, y, that was where the input was. But when I take the transpose of this, this input comes over here as a row, and the new thing that I have is actually a column, x, y. So, and this is now a matrix like this. So this right here actually represents the represents this part as a bilinear transformation. Notice you could actually do this out and see that it really does work. We could even use our trick from another video here, where you have, if you think like x times times that, and then y times that row, and then you have like x times this column, and y times that column. Notice we end up getting, actually, you'll notice it's not quite right because we're getting double what we need, aren't we? That's actually because of this fact. You take linear part over 1 factorial, bilinear part over 2 factorial, trilinear part over 3 factorial. Kind of like you exactly what you do like for a Taylor expansion if you're familiar with Taylor series. Um, so that's how that would work in that particular case. So we end up getting, so we take this, but we have to multiply it by half. So so I'll erase what I just did. That was just in the evaluation because then you add up the entries when you're doing that. So what I could think then is I could just take 1/2 of everything. And then that's the bilinear part that I desired. And that represents this as a result of a bilinear transformation. Done with that part. What about this y cubed? So we do a very similar thing. Okay, so let's start. The question comes like, how do you represent the third derivative? Right, well, okay, so this y cubed. So we take the first derivative, 0 partial x, right? And then just 3y squared. Then you're going to transpose this on its side and take partial respect to x and then y. So we get respect to x is 0, 0. Respect to y would be 0, 6y. Okay. Huh. Okay. So right now you have something like this. And if you had plugged a value in for y naught, you'd have this. And your input currently would be, you'd have a row and you'd have a column. But we're going to take another, every time we take a derivative, we have another input coming in here. Notice how I transposed before. I'm not going to do that this time. This time I'm going to keep these alone, but in my additional dimension is just a stacking. What I'm going to do is I'm going to think one level, then a level above it, and my next vector coming in is going to represent that stacking mechanism. The top level will be with derivative with respect to x, bottom level derivative with respect to y. So I'll have an x paired with the top and a y paired with the bottom. So when I do that, so let's see the derivative of this. So the bottom level derivative respect will be derivative respect to y on the bottom. On the top, respect to x would just be a 0, 0, 0, 0, 0. Ah, okay, so it's a stacking. That's at the top, that's at the bottom. All right, and the stacking mechanism, and I'll just kind of draw it ski-wampus like this, x, y. So the x will be paired with that, and the y will be multiplied to that. Now now remember we have to do this trilinear transformation. We will have to, okay. So this x, y, and right, okay. So this x, y actually, well, this x, y, let's just remind ourselves what this is. This x goes to the row, first row. Well, notice the first row is actually multidimensional. Zero, it's like a plane, 0, 0, 0. So this x actually goes to that plane. This y actually goes to this 0, 0, and that 0, 6. This x right here goes to the first column. There, this y goes to the second column. So if you want, you could actually use our technique where you just multiply in all these things to where they actually go. X to all those guys, y to everything on the bottom. Okay, from this. Now this one, x to everything in a first row and y to everything in a second row. You get a squared. Okay, then you get, so for this, for the columns, you say x times that, okay, and y times all of the things in the second column, and you get a y cubed. Now notice that if we divide this by 3 factorial, we end up getting the trilinear part. Okay, so it looks like the trilinear part divided by 3 factorial would end up just being, we have to divide that 6 by 6 and we get a 1. So this is our trilinear part. Trilinear part, bilinear part, and linear part all represented as multilinear transformations. Thanks for watching.